true. Okay. Let's start with the recording the lecture. Now, when we use the display, and I would like some people to hear. I know my lens. What is that? Once started, or let's say those problems, and it's going to be like this. I think that our next just really just really just share some of the material, and then I will invite people to contact me or any information requirement they might have about the course or time or anything in order to show. So today's lecture, this today's lecture, will be to record basics on public key cryptography. We have learned about to public key cryptography for it will be more effective in the so-called effective. I do not know what the people think that the school already know about the RSA, the animal changes, and the well external analysis. So what I will try to do today is that just talk about about this sequence. Why they are why how we use that in order to obtain encapsulate them from cost, and then why there is a problem when we think about what this is basically the figure and the program of the course. Okay. Then is right. Then one public key. Two, quantum computing. One is why three, false. And the idea and focus is on not the states. As well as mechanism of cold release. Clearly, the course age is self-contained. Well, I really serve some of it. Except it can be presented by Professor in third course. And if any of you follow the third course like photography, then that might be about the three goals, the salad of weeks, the basis of this. Well, so this is still and basically like goals for the days. So today it will be about key, more part of computing, and then the last 2 days. And false quantum theories. So, what is the scenario of cryptography? Classical scenario of cryptography is the scenario which the communication in a pair of adversaries or in a pair of enemies. A traditional model is meant to people which traditionally called as bomb. So, honest. And highest one percent. This is first problem of communication theory, basically to guarantee that the message reaches the wrong. But in our scenario, we have a solita tutto, and he is usually called even, which want to do something on our message. What is it that he wants to do? Well, it depends on the scenario. So if our protocol is protocol is guaranteed the integrity of the message, if we might want to alter the content of the message in such a way that God is unable to recognize any change. Or we might have feel that God is stop the message or that is the scenario of the reality. It might be that he was only the message thing. And us doesn't know anymore the purpose. So all of these scenarios lead to one confidentiality. Or individualistic, which is dealing with equal or other message or confidentiality. So that the problem of authentication. In which basically was that to invest for the so a message doesn't originate but it does originate but both is speaking. Now, I mean, this is the standard perspective for government and also about but I would like to point out that in a practical scenarios, what we have is that there might be some confusion of roles. So we might not be so sure that he is a different person. Because I didn't get sure. We follow thanks to you. Or I don't really sure. Both is a transformed person. I say it all the time, which let's try to explore that way. So there are plenty of scenarios in which is to self of the family of the what I call the saying honest person or that is issues factors. One of the side applications of recent photography are in devising efficient and secure motive systems. So if you want to develop electronic motive system, another components. One is the electronic motive systems which are actually the core station. Another family has electronic motive systems which are implemented on some of the products. We want to design system for actual electrons work then has been careful because connect it is used voting, which wants to be able to play when voting for that candidate in order to get paid, and actually one for it. Or it is the ones who currently calculate the votes, which are correct, and try to well, the word behind the word is basically the visual element, and it's a broader, so they're trying to alter the results of the election. And have protocols to avoid multiple scenarios. And I think that in that case, the role of the adversary is the first case in the results, and the second case here in the fall. So figure out these protocols would have to be clever and lay out. Now, the standard way to divide the field communication between us is to prioritize the moment seven aspect. Let's go take it. And then Einstein applied a summation to the bank foundation. APA on organization, normal generated ciphertext. He said that the cipher bond, and bond, which shares the same secret as Alice, lies the inverse by subdivision, also in order. The assumption is that even cannot meaningfully alter state because she doesn't know how to even going. She also either that she doesn't know key. If you assume that battery knows the key, then it's able. It's pointless to even see the answer. So, no security analysis about false either doesn't know something which is normal by now. It might be the public key or the BCA security. So this scheme provides the direction of data connection is designed super way is guaranteed with more confidence because you cannot recover without the and a form of integrity. Form of integrity because administrative form you cannot alter in the message state. He can find and change something, but then when the ball is going to hold the ciphertext received, he can find something meaningless. So this scenario also is. There's also a form of meditation because the KHC is known only by exception by Alice and Bob. So the fact that it is properly encoded in by scientifically, this symbolic is either zero or plus. So the little is that it can explain really for conditions. Let's these are some of the course that are provided. Okay. So we will if we read the course, very good. No one will see the comment. Yes. Okay. So I was saying we have a week for participation because in this Alice like authentication like Bob and Bob authenticator is but third party she would use the key as a authentication product to distinguish between Bob and Alice. So Bob could pretend what third party and vice versa. But this is a weak form of authentication. All about this. It's not an issue. Now, the evolution in the scientists has been waiting for the late scientists, and here we can go back to the because we then most of the people here so it's complicated. It's almost anything different than to go to the place, thinking about yeah, classical cryptography. Uh, People believe that the only way to see with your competitor are three character secret. But there are some leaders of the Rank Corporation, which is a corporation which is responsible for basically proposing the architecture which is the internet. Well, but I mean, but they are militaries. So they were and also the really the so well, this they suggest the main encryption schemes that could be used on robot authentication. And of course, that the most pricing problem is to share these things. And so they propose is the operator third problem of how the things have to be divided, how they have to be, how they have to be reflected, is to say changed, and so on. Anyhow, in the seventies, we had this idea, which has been applied both to part of the secrecy that's based on under the problem and to the system based on signal problem. But there is no need to use exactly the same evaluation of the equation. That is to say that this model of secrecy is a model of activity where basically you have to, in order to encode, you have to take the message, put it into the safe, then lock the safe combination, check the safe over the net, and then your counterpart will have a safe combination over the safe. In public cryptography, we are using the model of the lock. The difference between a safe and a lock is that in order to open a lock, hopefully you need a key. But in order to close the lock, closing a lock is something everyone. So encrypting, we don't have to be something which can be done hard, and at least hard. Decrypting, we hope, is something which would be possible only virus get vulnerability. The one and so the following we found is that basically even killing a ball, a kid, which is a parameter which goes from a state of the message. State of messages to the state of fiber. A function detail, it's not the same thing, which we want to be used to. So a state of fiber place, the distance, and exists different exists let's say in Brahmin, such that the encryption with the of the encryption with the message is equal to the message. So far, so but what we want is that the prime it is equal, it is computationally fast over take one, take that. Stop. That is the structure with that. And also, recover and form. Interesting. Well, the first is the problem component. So it has determine the public recipiency, so not the organ, if we just have the key close. So very good. That's not about. But I felt the need to add also this condition, the common message of encryption, because we can see that in some cases, even if you don't find the key, you can see the message. So this is something which we can do. Also, in the secrecy cryptography that require these things we want from the example. But there it's somehow clear, for example, we should expect. If I want to keep cryptography before I forget about this, then it might take up with some very, very important information. So, this. A few remarks. The first remark I would like to make is that in part of cryptography, the problem of confidentiality, the problem of data pledge authentication are in a sense that while we did a cryptography, knowledge of the sequence code was not guaranteed identity of person coding. Here, everybody. So if I want to send a message to Bob, what I should do? I said, yeah, yeah, pass, recovers the key line from Bob. She generates C and only with file fails Bob, and Bob recovers N, which is recalled with T data of this. But everybody, so a time Bob received a message encoded with the family key, doesn't have anything about the. Well, one of the basics of this kind of cryptography is the notion of acknowledgement. So how do you read a public key out of a secret? You need some function which is easy to read, but very hard to read. Only occurring completely almost invisible. Almost because I think the computation because all of security is clear here. There is a link in the it's true that we derive of the data, but we derive the time from something which is so that's valuable. But on the other hand, it is not so obvious for but we can recall the secrets usually again. We can, but what we want is that the time required and then populated people is so long as to make it basically not feasible from a regional policy. So for all of them, what we want algorithms for which there are no polynomial time solutions. That is to say, we want that time. storage. Keep keep something from keep only as like we want like so first require this it requires too much. But again, I require that it is larger or less when you say it. So, let's say, well, it's stay or not. So basically, they see long enough, as a relative, but our factors might cause of system, but it might require like the order of 10 to recognize. And then we can not have this. Now, it's clear that this requirement that basically it's easy go from K and T divided half T divided. It's an requirement that which is not so simple. But basically two large families of systems that we use nowadays. One is based about the number of theoretical problems and the poster algorithm on this kind of systems is parasitic. The third one, so is the number another kind of algorithm are taking with the element growth and persist, which are built about and in particular the development is legal. And these are the ones which are raised. And they is the sort of standard, so there is just one big implementation, I would say. There are variants, but they are more of a deeper than after user. Poi insieme dal canale several playlist of groups you can choose. For instance, you can use groups which arise from fine theater, or you can use groups which arise from the curves, and you can have different computing models depending on you are choosing. But in any case, the ones which are used in practice, the either to the family balance states depend or whether of the discrete law. And if we have actually used, let's say, that classical computer, so anybody has nowadays, then some very good balance of the complexity of grading demonstrated and neural. So we have an attack on how long has to be in order to have reasonable activity, and somehow we are very efficient and don't manage the manipulation of these things. So everybody will a payment with the credit card, every time you can say it, unless you put that, whatever, every time you use the computer, sign for nowadays, also molto information for America quindi questi estero okay? Well, we use either of these systems. What's like formal is that basically probably computers, which are very common with a very native technology, which doesn't have a bad name, particularly nowadays. Okay, people say, perhaps a quantum computer will be able to dot, but we don't know that the name quantum algorithms. So nowadays, even if we were to have a quantum computer, there are very many things to do with it. But also, the Aristotle and also the below. So the only thing we make to say we are very still quantum computer, very okay, you can always go more than sometimes with each other. That's what the quantum computer is going to be able to do. That parametric will be also able to do something else. But it is, it can definitely provide you that. There are time books which have been published this year about the quantum apocalypse of this effect. We are reading through a kind of I am not sure personally that the quantum computers are going to be we can commodity hardware in action. And in constructing a quantum computer, as we can see, it's hard, heavily trying is harder, it requires quite dark mass, and requires a very controlled initiative that work properly. So I doubt that we have our lifestyle, quantum computers which have the size of a life from it would create it and no others quantum computers are here to stay, and we can assume that at least some actors eventually that they take the exact answer might have super. And why do we people concerned? By concerned answer, that's because these algorithms are used, as I mentioned before, not only for person-to-person communication. Well, let's be honest. Okay, I would love if people were to take in mind what messages, without apparently they are good, but after all, they are not completely so actually use machine also their meaning of knowledge doesn't find out when I said, okay, keep that nine rather than so that means that wouldn't be so much of most of concern. But this happens also used almost part of the programs used for 9,500 banks or for basically evil that so this algorithm, breaking this algorithm now empower third party, for instance, either the result of the network process. And that is finally yes, Misha said that would be more than willing. So we have partner should be careful with this. But before we get to that, the concept
No, he did.
ah,
He interrupted that. And it's like the, it's
okay.
full story. He had any question? He right.
Absolutely. And then we see how to fix this together, right? Well, so, we find figure out it's so okay. Just say as field which is followable well. Are you familiar with say from and say when you need some right and thought? Don't say it's not but me. That's not for me.
Something that happens to them. They can see what the feeling.
Okay, I'm not your on you. Say that's what we call basic thought. Say because it will be per time to be interesting, or to do what we speaking after. First of all, I would say if they is a formal idea, let's see. But it is easier given to numbers, teenage, return, and she's going to follow you. Well, given the so easier to multiply prime numbers we say together, then to determine even how how it is done. We should already know the problem of the problem. Determine the designs. For multiplying numbers, well, there are algorithms which are very efficient. They are even more efficient than what one less than. So the complexity here is less than and square. And for the number of iterations to do is actually the order of, let's say, order of if you have the same factor the same size, is the order of p to the 1,7 7 whereas the basic is which is taught in school, f of x is the order of p squared. Compared to the fact that p squared is in order to be. Given anything further factors, let's not order for which no has polynomial and there are some very probabilistic algorithms, but they are not all probabilistic. So the idea is that the fixed function, the function given by the might be unknown factor. Function, then we will say before, but it's easy goal of the question should be part of here. But it's hard to go from here, which will be a center of a secret. This is the first agreement, say, second agreement, are basically two algorithms, which we use. The first algorithm is that if we get and second algorithm is the category screening industry. These are essential because they are part of the computation people have to do in order to derive the system and we don't want derive the key that in order to see. Let's start with 9 theory that doable, achievable in a regular flow. The third ingredient, which is the reason why LSA works, is
This,
the way
really at all is not leaves.
oh, when I know how many people are together. So, we have two people there. That's good. Let's see what it's not being that big. The screen. Now you see the screen of yes, 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 yes. Now you see the black dot on for your what I investigated. So say there are these two algorithms which you can use, and both of them are polynomial. Sheets. And then what else that we need? We need some theorems. Basically, what we need that is some concept. Function, which says that the function. Oh. From the H of G person. Okay. So basically, these are the ingredients with that LSA. I would like to say that LSA system is very effective. And in a sense, it is a kind of quite a simple system. There's plenty of programs. I will use it as is, but somehow the idea, the name of the system, obviously bringing it, is something which is very, very. And the point that we take is two others, which are efficient, is something also which is very important because before really fast, be able to have an algorithm which we can use in practice. When we shall speak something about frequencies testing or market, we see that we can provide also what previously told, we can provide a reasonable margin to each of the work. But with the work, they also are much more elevated than these things. What are the two algorithms? The first algorithm, for Cleveland algorithm, interpolate what understanding one is so vast in time. That was okay. It's just the time that word no correct. The Cleveland algorithm given to mathematics, they sharp and it's like the greatest call of the life. Now, in order to Germany, the biggest goal in life and that was at least in high school, really, for which is I would say complete of the conversation is involved, which is the factor A, and then we have the factors with the low, the power factor with the lowest extent. That works because the definition of the biggest organizer who feel that for peace the definition way to start with the organizer. But the reason that work, basically that's the exponential function. If RSA were to be based on that, we would have a code with generic exceed. It would be equivalent to greater than this. So, what we basically are going to do? Basically, here we use the standard appropriately related to solve without virtually called VCD is a number B such that B divides A and B divides B times although B divides such that B divides A and D divides B divides B divides B divides this is the definition of this class. The value if we are creating integers, always two values called one is positive, the other one is. So we usually take this type of the value of the positive values called. But in order to compare this function, basically what we do, we'll start off by the full phase and basic properties, which are easy. In ECD. And write the following and hopefully it's repeated. It's equal to G C E. This is the first one. The step number is G C E. A, comma, 0. Is equal to A. Let's get it. Zero. Obviously, 0, 0. But further is like GCB A, B is the same as GCB. We made A of B. We converted I now to divide the emission factor. Because what do we do? First of all, if A is not going to be forward, forward, now we can define that. So this is what A if B is not then we will use the C B bar with walk away. We just walk away. So the first term we have to is the largest. Then if B 0 then we just use but we use for two. Play overwise, so all of this local repeated, we just return the PCB, the real small between them. Take B and the remainder of A divided by B. And you can see actually, I invite you to check why 50 verified that this algorithm actually works. And this algorithm we converge that's one. Because the number numbers here decrease the quantity. Actually, this is perhaps one of the most important algorithms which we can have. There is another DPD algorithm. I was right there. Maybe because first we will see a different kind of algorithm, which is still very efficient. This is like this. But second, because well, just find it, which means answer, which is a called the failure. And it's the which returns what three numbers, which are G, alpha, which are basically D the GCB. Yes. Yeah. Maybe that we I wrote a big, and then alpha and beta are two integers. You grade one level from your one standard go to ECD is 90 should value less of the order. The minimum between the minus 1.0. G is this, and then alpha and beta such alpha plus beta is this equation. So what the thing is freedom angle does is solve this equation, the equation S like say plus y plus c equals the GC into A. And this is the in integrals. If you are working on the natural numbers, real numbers, or like that, well, this is a linear equation of right one to another. So always manage solutions in the solution. So you can focus at the top. You want very solutions. Or to very it's all with the tools for life that they have after also first. I think that is here. But we are going to look for solutions. They need a house. We need a picture. But the nice thing is that these are the connect to the table. So solve a linear equation of rectangle is easy. So, right? Okay. Let's get back now to planning this slide. Thank you. Here you can answer. Here you can follow. And Volvo is the one which has to learn. Volvo is rather well, let's just take why I would advise you for and then agree having which is people times. Then we do need the verb, let's say change that's very good. P it's not the balance. And Q and also is P and equals P minus one. So
Black.
right on the
Let's see.
if you can see the black border, you will use the black. Because this is correction. Okay, let's take it. Now, if you can see the blackboard, I try to write, large on the blackboard. So here we have Alice. Here we have Bob. Here we have Bob picking two primes, P and Q primes. He computes n equals PQ. Then he chooses E integer co-prime with P minus 1 times Q minus 1. And compute, well, we can say Fn equals P minus 1, Q minus 1, is that number. And Bob uses the extended Euclidean algorithm in order to determine D such that E times D plus K, where K is any unknown we might have, n equals 1. is to fly. So I try to see whether there is a black body which works better than this. That's very difficult to stop people. But there should be a way. Yeah. If I do this. This works, guys. No, it is not share. No. With these, yes. Okay, what we can do is, yes, we can always take the penalty, yes, but we just take text that honestly and confidently. Because that's easier than think five, give for a time before. Browser. Okay, let's look. This. Keep those. So,
Can you stop?
yeah, but just speak out. The root, I know shit the bibliography. Please, you need to after extremely festival. And I call them here what's able to say. Okay. I just give the facility share so. So, okay. I'll say. Well. It's a quarter of an no. Okay. It's been like, oh, no presentation. Let's say, 405. Sure. 405. 405. 405. Yeah. We're always enough for the was 405 plus 20 for 25. Okay. So we just create these amount the sleeping one. Oh, yes. Oh, here there is after I was that's right. Right. Okay. I'll say designer. We take two primes. We take an exponent, which is co-prime number one of -1 to 1. Here in the co-prime for the there is no, but in this case, he would rather have as a people rather creative on the fine. And because we did a problem here, and that is a picture algorithm, which is e to minus one was p minus one t minus one. That is the inverse of the exponent we have here. Modulus is p minus one. The reason why the vector are basically first, how we take this inverse, we take this inverse basically, but you give a p again. And also writing the order because we have d we solve dE plus k p minus one. Is it p minus one? Whatever you read here is it p minus one times q minus one. Even and technically the ingredient algorithm we always solve these. And this is time further to why we don't run the one? Because this is the order of the loop when we really works. Actually, you can go and do it as the way LSA is presented here. We see that what the system does is not working like really efficient. We can the bottom is assume that I will follow that. But it works in the typical group of aggregate from speed, which is already required. In the typical group of aggregate or on the speed, which is already required. And it uses and we do it as we are on the speed. But puts anything together. But that's exactly right. But you can check where the final key is either by E, they take some component N, which is anonymous, and the secrecy is either by the different. Knowing the value of the file actually swallow. And observe that if you know N, you don't know P swallow. Know that you recover human flying, human flying, you need. Maybe it's the same way we are. Now, in order to filter, here we are, for electronic key, the encryption of message is that's the message rise to the people record to a public record. The related message rise to the people record points. The encryption is rising what we receive to the teacher's fault and what we want. So these two factors are important as it will be on this. Now, and the worst point that was there before of the mathematical theorem, negotiating with the neighbor's theorem. But what we like to class is that what we are actually doing here is rising the message from unwell and involved and confusing the group of the cycle effects that we already report on the message. So it's like again, steady and calling is start encoding is N, which goes to what's the question? non mi ricordo, questo è questo non è quello, no. A quel punto calcolare chiusi il computer. E come ti rimane il computer? Allora, allora, no, e come and cheese, non è meglio. Meat and almost anything. Every computer, anything. Cheese. So that license. They call it, you start on C, different pen, whatever you see, they complete the C, one, over, equals C, the B. So if I call is right per hour, it's calling is computing the atoms and each root that overlays. The point is that computing each root and goes on here, and I get here, and I get down because it's having a pair say is the same as the root BC, which is an integer, meaning an integer is small, and maximum. Why am I interested in this factor? Because this suggests the fact that there might be many ways to call the nationalist center actually. One way is to know the a very general for instance, suppose that the end to the E is less as a number, not as a military part, is less and you know it. But then as you get is equal to integration. It's an integer. And then you might try it's the key for your of a message C, which is what we did. And we call that the later of the timer. We have an heading for that's all. And this is one of the reasons why when one is using MSA, one has to be very, very careful in terms of also, I said, evidently is an element of the N, correct? Well, we could choose as N one, and if they call it equals one, or as N zero, which is a perfectly reusable the N, and then they call it. This kind of factor tells us basically to store RSA is equivalent to be able to complete a group in these really discussed. Are there any efficient ways to say what without going into conversation? No. As of today, there is nothing more than aspect. Actually, we have rules that involved. We can rule and we can complete square root each here. Then you can are there any questions? I know that the last part, rules. But we gave it time for the same regulations too. That basically find quick that I hope that with that being placed against otherwise for the 1,900 so in fact you can use RSA also to do I think quite different from what we had for the advantage of that. But before getting there, first of all, we get algorithm. Then we also record them. Okay, and that's the rate of Python, and see whether we might make it without making more efficient. So, what's going to using the yeah, you'll never how it goes later now. What's a copy of something, why, Ci sono? Ok. Guarda se c'è. Can you hear me? Yes, professor. Good. And I can hear you now. So that's already an improvement. And then the other thing I have to do is to share, clean, window. Let's see whether now it works. Share. Okay. Right. Oh, yes. And now this. So share. Okay. Stop sharing. So next share would be, let me see, let's say. Oh, I think it's a definite improvement. Good. In meantime, I'm just rewrite what I was writing before. RSA. Sorry, let's see. Encoding. We start with a message inside N, and we obtain C and we decoding. We start with C inside N. We obtain M, C, 1 to E. Okay. This is what it's really better than before. Let me also do something here, perhaps, which I can do. Because here, go. Yeah, okay. Where do we want to go? Yeah, okay, good. So from tomorrow onwards, we shall use my computer and not the one in the room. Okay. Good. Let me see what I was looking for. But okay. Okay. I was very sure we had that, but okay. Shall we resume? Okay. GCD. I was looking just for one thing. If I have it handy. Okay, but I have it sort of handy. So I just show a
a few things before we restart. As I was telling you before, basically RSA corresponds to solving the problem of raising one element to a given power in this ring. So in the ring of the residual classes modulus n over an element to the public exponent in this ring, and decoding corresponds to, as I wrote here, computing a sort of a root. And the point is that basically computing roots is something which is equivalent to knowing the factorization of family. And this is a not straightforward thing, and it has been used also in some algorithms or some which are called say once more a bit about the Euclidean algorithm and RSA, here that now I have a better support than a few minutes ago, and then move about oblivious transfer, and so why RSA, even in this context, can be useful. So let's start with RSA. And let's see just, let me say, Python implementation of RSA. Where is it? Let's go here. So stop sharing. Share. RSA. Share. Oh, and I think that now you see an actual implementation of RSA. The Euclidean algorithm, as I said before, can be implemented in a very simple way, in a very straightforward way. So it's just 3 lines of code. And that is something which ends up being handy, because when we want to implement RSA, the key gen in our case is done like this. So we compute Euler phi 2, which is p minus 1 times q minus 1 in our case. And then we use the extended Euclidean algorithm, which is the one which gives us also the solutions to the Diophantine equation, in order to recover the decryption exponent. And then when we want to encode, basically we raise the message to E, and when we want to decode, we raise the integer to a message we received to D. And that is the simplest way to have RSA. There is also a different way to implement RSA decoding, which is by means of a Chinese reminders theorem. Actually, you use the Chinese reminders theorem also when you prove that the decoding of RSA works. But the point is that the Chinese reminders theorem tells us when we can link solutions modulus P and solutions modulus Q. And in a sense, it's the key of the algorithm which I will present presently. Oh, sorry. Why doesn't it? Okay. Why don't you like? Okay. Yes. Where we are. So, Chinese reminders. Suppose P and Q integers. Greatest common divisor between P and Q is 1. And then that we have x, you look for a value x such that x is equal to A mod P and x is equal to B mod Q. So what do we want is a value x which is A, when you compute, is its remainder modulus P. It is B, when you compute its remainders modulus Q. The theorem tells us that there exists exactly one solution, let's say X bar, between 0 and P times Q. This is the first part. The second, it is easy to compute X bar. Now, the proof is based upon some algebra. I think that if you are following the course in coding theory, you will have seen, or you will see, this algebra, because it's based, at least when P and Q are primes, you can do that using the algebra of finite fields of order P and of order Q. If P and Q are not prime, then you can just recurse using the same theorem, and you end up with the same result. So I just mentioned how this X bar is obtained, given that assume PQ primes, and both prime. So ZP is a field. So every element here admits every element, non-zero element here admits an inverse. ZQ is a field. And then this means that P mod Q admits inverse in ZP, in ZQ, and Q mod P admits inverse in ZP. How do you obtain these inverses? Well, it's easy because you solve Px plus Kq equals 1 and Qx Qy plus K prime P equals 1 using the Euclidean algorithm, and that you can always do. So now you build up your X bar as, so let's say that this inverse is P bar and this inverse is Q bar. And then your X prime is Q bar Q A plus, sorry, Q bar Q mod A, yes, Q bar Q, P bar P B. So if we do reduce this modulus P, you see that the second part, this part, is 0. And this is 1, because Q bar times Q is 1. Okay. Here we see. And so X bar is exactly A modulus Q, the modulus P, sorry. And if you compute this modulus Q, then the first part goes to 0. P bar times P modulus Q is 1. And so you end up with P. And this is a nice ingredient because it's what basically tells us that LSA works. And this is whence the phi function we have seen before comes from. Because it tells us that basically, in order to compute x to the d, let's say, modulus p times q, we can just compute x to the d mod p, and so we obtain x1. Then we compute x to the d mod q, and then we obtain x2. And then we can build up these two solutions in order to get something which holds modulus p times q. And as you can see, I mean, even if I'm going very quickly about this stuff, this kind of construction is efficient because the Euclidean algorithm is efficient. Now, let's move to the problem of oblivious transfer. The problem is Alice asks Bob for some information, but Bob does not know what Alice has asked. Now, if we put the problem like this, and actually Alice gets the information, gets the information. So, if you wish, this seems a very weird kind of problem to pose. I mean, why should we do something like that? But we can think about the following scenario. For instance, Bob is a newspaper, and Alice wants to buy one article she wishes to read. But she doesn't want her reading habits to be tracked by the newspaper. So she says, okay, I'll pay for one article of your journal, whatever that is. I want you to deliver to me that article, for otherwise I will not pay you. But I don't want you to know what I've been asking for, because if you were to know that, you could trace my habits, or who knows, perhaps Alice lives in some places where people can be monitored if they ask. I don't know, whatever. But the scenario of we don't want to be tracked is a very realistic scenario, thinking about what's going on with the internet, even nowadays. And this kind of protocol can be implemented with a function which is basically a so-called 1 out of 2 OT, where Alice asks Bob for information which will be delivered with probability 1 over 2. That is to say, we are going to build up a sort of unreliable channel, because it's probability 1 over 2 we get the information, but in such a way as to then implement the protocol I mentioned before. And one of the ideas is the following. Basically, to use the RSA algorithm in a sort of unconventional way. Now, let's make a remark. A bit of algebra, not too much, but just what we need in order to get where we want. Let P and Q be primes. N is P times Q, and we define by Zn, symbol I've been using the same symbol before, the set of 4 integers 0 from 0 to n minus 1, with sum and product, where sum is defined by a plus b is by definition the integer a plus b reduced modulus n, and a times b is by definition a times b modulus n. This, where by modulus I mean the remainder, and I mean by remainder I always take positive number. So these two operations are actually operations from the set 0 and -1 into itself. Then it can be seen that this algebraic structure is a ring. These operations are well posed. We have a commutativity for both sum and product, which comes from the commutativity of sum and product in the integers. We have also that every element admits an additive inverse, and that's not a problem. And then we have that every element which is co-prime with n admits also a multiplicative inverse, and that comes from the Euclidean algorithm plus, or if you wish, from the Euclidean algorithm and the Chinese remainder theorem. So this is a ring. We have also the distributive properties. So this is a very nice ring where to work with, and many of its properties are similar to the properties we have with the integers. Many, but not all. In particular, we can consider the function from Zn to Zn, which sends an integer x into the integer x squared. And what we end up seeing is that half of the values we have here, roughly half, are squares, the other half are not. So far, so good. But if we want to consider the function which goes from x, the inverse of this function, then we have a surprise. The surprise is that basically over the integers, well, the square root of an integer, there are just two possible square roots of an integer. So if you take a square, let's say 4, its two square roots are -2 and +2. And this is an essential part of the nature of the ring of integers, and then also of the fields you construct out of that you cannot have more roots to an equation of the kind x squared minus a equals 0 than the degree of the polynomial you have on the left hand side. Well, in Zn, things are much messier. Actually, in Zn, given an element, let's say alpha squared, belonging to Zn, so we start with a square, non-zero square, possibly because if it is a 0 square, okay, the only possible root is 0, then we end up with 4 possible roots instead of 2. And this, at least at first, is quite surprising, because you have a degree 2 equation, which is a legitimate degree 2 equation, which has 4 roots. How do you obtain them? Well, the idea is to say that suppose x squared equals a. That's your starting equation, mod pq. We can decompose this equation into x squared equals a mod p, x squared equals a mod q. Just because we are working modulus p times q. But then, if we have this, zp, as I said before, as well as zq, are fields. And then here we see that every element, every square element, feels, okay, p and q different from 2. Just because if we have one field with 2 elements, then there is just one element which is non-zero, and that is exactly one root, which is itself. Okay, p and q different from 2. And here we see that a admits, if a admits there is a square root epsilon, so epsilon is a, epsilon square is a, then p minus epsilon is also a square root, because p minus epsilon square, here we are in a field, is something p times something plus epsilon squared. So we see that there are two solutions for this equation. Two solutions for this equation. Chinese remainder theorem. We build up a solution modulus n, and we end up with 4 solutions mod n instead of 2. Well, that's quite surprising. At least to me, it was quite surprising the first time I saw this, even if there is nothing especially involved in this construction. How do we build a crypto system or a protocol, an oblivious transfer protocol out of this? The idea is, here we have Alice, here we have Bob picks P and Q, PQ primes, N is P times Q. And then he sends E, there is a message which he wants, or perhaps wants not to send to Alice, wants to send to Alice with probability 1/2, and then he computes C to the E equals M mod N, and sends to Alice C and N. If you wish, you can also send E, which is his public key. These are the elements at this stage. These are the elements Bob sends to Alice. Now Alice wants an oblivious transfer, wants to be able with probability 1/2 to decode. So what does she do? She picks an element, let's say alpha, belonging to Zn at random, not 0 and 1 possibly. And then she computes alpha squared, what equals to f. And she sends f to Bob. Now Bob knows P and Q. So Bob can compute the 4 computes the 4 square roots of f. Let's call the beta 1, beta 2, beta 3, beta 4. How does he do that? Well, basically considers f mod p, f mod q, computes the square root of f mod p and mod q because using the Euclidean algorithm, and then he ends up with these 4 numbers applying the Chinese remainder theorem to build up something modulus n. Now he picks one of these values, let's call beta equals beta e, and sends beta twice. Now, what do we end up with? Alice has alpha and has beta. There are exactly 2 possibilities. The first possibility is alpha is plus or minus beta. If alpha is plus or minus beta, then the only thing Alice can say is that she hasn't got any new information at all from it. So she couldn't decode the message before, she cannot decode the message now. But suppose beta different from plus or minus alpha. What does this mean? This means that alpha plus beta is different from 0, as well as alpha minus beta is different from 0. Good. But alpha plus beta times alpha minus beta is equal to alpha squared minus beta squared. And this is 0, because both alpha and beta are square roots of the same element. But what does this tell us? That alpha squared minus beta squared, the greatest common divisor between alpha squared minus beta squared and n must be different from 1. And in order to persuade you of this, think that if this is 0, this is not an invertible element, modulus n. But all elements which are coprime with n are invertible modulus n, using the Euclidean algorithm. So this GCD must be different from 1. But n is p times q. So either the GCD is p or it is q. In either case, Alice finds out p or q, and then n is p times q, so she also finds the Euler prime, and then she can decode RSA. So this is an example of an algorithm where Bob provides some information and he has no idea whatsoever whether this information will be useful to Alice or not. It will be useful with probability 1/2. And this same protocol can be implemented in order to basically, how do you say, basically to exchange keys between Alice and Bob in an iterative way, keeping some bits in escrow. What is the idea? The idea is that both Alice and Bob implement the same protocol. They have some keys. Think at these keys, for instance, as, I don't know, as signatures on a contract. And the idea is that Bob needs Alice's signature in order to get the money, and Alice needs Bob's signature in order to get the house. So basically, they have to sign the same contract at the same time. But it's also true that Alice and Bob, perhaps they live in different countries, we are using internet protocols, whatever. And so the point is, how can we be sure that they will sign at the same time? We cannot. We cannot, for most of the signature protocols we have, basically requires one of the parties to sign first, and then the second party to sign second. It's the same if you have by a notary or by register, and then you have to sign for something. But there you have a public officer checking that nothing unsavory is going to happen. Whereas off the net, that's not sure. But what's the idea? The idea is that basically both Alice and Bob exchange their signatures using this oblivious transfer protocol. So after the first round of the protocol, both of them will have roughly half of the bits of the signature of their counterpart, but we won't have all of its signature. And then what they do? They declare to each other what are the bits which are missing. And then they do apply the same protocol, both Alice and Bob, in order to get half of the remaining bits. And they go on till they have a complete signature. What is the nice bit about this protocol proposed by Sean? Basically, the nice bit is that if one of the two parties decides to interrupt the protocol, says, okay, I will draw because I have enough bits, then the bits missing to its counterpart are more or less the same he has. So the effort to construct the complete signature, for instance, by exhaustive search on behalf of Alice and on behalf of Bob, if either of them interrupt the protocol, is the same. So basically, if one of the two is cheating, the other part can cheat as well and get the money or the house. So this weird kind of application, basically, of RSA, because it's something, yeah, it's also something which could be considered, let's say, usable, and which could be defeated if we were to have RSA brought. I mentioned before And here I will also show an oblivious transfer protocol about D-log based algorithms. What are they? Basically, D-log is the problem given a group. Oh, no, it's much more pleasant to write here than there. G, let's say, generated by an element G and denoted in a multiplicative way. For instance, the multiplicative group of finite field or the group of points of an elliptic curve. I mean, there are many groups which are good for this kind of problem. And given, sorry, G age, which is G to the alpha, determine alpha. So we have age, we have G. We know that age is a power of G. We want to find alpha such that G to the alpha is age. And this is called discrete logarithm problem because if these were to be real numbers, alpha will exactly be the logarithm of age in basis G. Now, what is, let's see, one public key algorithm based on D-log, and example is Ergamal, because it's also what I will be using for the oblivious transfer. Here we have Alice, here we have Bob. Bob chooses alpha, secret, exponent, and has, let's say, small b, which is G to the alpha. There is a group G which is known by everybody, and sends to Alice B, which is his public key. Alice has a message M belonging to the group. She wants to encode M, so she takes k nonce, that is to say, an integer chosen at random, and then she computes G to the k, B to the k times n. And let's call this xy. And xy is what she sends back to Bob. Now, Bob, what can he do? He can just observe that if he computes x to the alpha, this is G to the k to the alpha. But this is the same as G to the alpha to the k, because all the properties of powers here hold, and this is equals to B to the alpha k, which is, sorry, B to the k. So x to the alpha to the minus 1 times y is B to the minus k times B to the k times n, and this is the message. And in this way, Bob recovers the message. As with RSA, this is just a sketch of an algorithm. The real algorithm, if you want to actually use Ergamal for encryption, should be implemented with extra care. For instance, you don't just encode a message like this, but you encode a key, because it's better to encode something which has no semantic meaning. Otherwise, there are some attacks where you can recover some of the information about n from 1. So, but the basic protocol is this. If you can solve a discrete logarithm, you can break this protocol. Is breaking this protocol equivalent to solving discrete logarithm? The answer is no, as with RSA. It's the Ergamal problem given G, B, G to the K, determine B to the K. This is the Ergamal problem, which in some cases can be solved. In other cases, let's say that if a group is chosen well, it cannot be solved. And now let me move to an example of oblivious transfer with Elgamal. Here we have Bob, and here we have Alice. She wants one message of her choice out of n. And Bob, here, what does it do? Okay, so here we have our messages. Let's say M1, M2, Mn. Here, Alice picks alpha. Okay, and here we have beta. And just a sec. Yes. So I use the same notation as here. Just a second. I just want to use the same notations as here. So I use the same nonces and okay, here. Want something. No. Sorry for. No. Oh, thank you. Here it is. Okay. So Bob picks beta as random. Yeah, the notation it was correct. In any case. And then he computes V, which is G to the beta. Exactly as if it were an Elgamal key. And then he sends V to Alice. And here Alice has V. Then Alice picks alpha at random, as I was saying before, and computes U, which will be G to the alpha, in this case, V to the V to the minus I, where I index of the message. And she sends U to Bob. Now, what Bob does is to generate a series of Elgamal encryptions. How? Well, basically by picking an element W, J, which is equal to U times VJ. Oh, sorry. VJ for all J. So this is the element Bob builds up, and then he generates an encryption of the kind G beta, because that is the element which we always used. And then here we have WJ, okay, times to MJ. And since, well, G beta is V, so it was already known, WJ, MJ to Alice. Okay. Let's go. Now, what happens? Suppose J equals E. Then WJ is U VJ, which is equals to G to the alpha, VI, V minus I, times vi. So it is g to the alpha. And then what Alice does is Alice knows alpha. So Alice computes g to the alpha to the -1. This is xi yi times yi, and this is exactly mi. But if j is different from I, then g to the alpha to the -1 j is equal to where was it? G to the minus alpha V to the minus I Vj. And now we sorry. Well, I wanted to write Wj equals U Vj equals G to the alpha V minus I Vj equals G to the alpha V to the j minus I. And now the problem is that Alice doesn't know what V to the j minus I is. So whereas here, Alice can just invert, because the element we have here is g to the alpha. What we have here is that she has received g to the alpha, v to the j minus I mj, and she has no way to know what this element is, because she knows g to the alpha, but she doesn't know what v to the j minus y is under the Diffie-Hellman, under the RMR assumption. So what we end up with a protocol where Bob sends exactly 1 out of n messages to Alice, and he doesn't know what message he has sent. Alice receives exactly 1 message, and from her knowledge of that message, she cannot recall or she cannot infer any information whatsoever about the remaining messages. So this is, for instance, the scheme or a scheme where the of newspaper, but we don't want the editor to know what is the paper we have bought, works. Applications of these, there are many applications of the same protocols, also to things like the millionaire problem, in which you have to compute a function whose inputs depends from the data of Alice and the data of Bob, but neither of them wants to reveal their data to the counterpart. Or, I mean, there are many protocols based on oblivious transfer. There are also protocols similar to these, which are zero knowledge protocols. So basically, we have protocols where we have to prove to a third party that we know something without revealing what we know. More or less the same as many university exams, where basically you have the professor which knows what you should tell, and then you should do, for instance, some written part of the exam where you show that you know the theorems by applying them, but without writing in full the text of the theorem. So that's the kind of zero knowledge proof which is used, for instance, in protocols of, well, also voting protocols and cryptocurrency protocols. I mean, there are quite plenty of applications of that, which, how can I say, yeah, are currently used, and would be broken if we were to break RSA and LMR. So what we should see tomorrow. I mean, if you have any questions, please ask now, either now or tomorrow morning or whenever you want. You can also write me an email. But what we will see tomorrow is that what is a quantum computer? I don't know if as any of you taken some courses on quantum mechanics or is familiar with quantum computation in some form. It's just to ask.
No, person, no, professor. I don't know very much about physics either.
We just see the basics, but in a sense, what is enough to see what a quantum computer can do, and also what a quantum computer cannot do, because in practice, we have seen many times, I mean, there is this behavior that a quantum computer is supercomputer. So it's something which can do plenty of computations, solve all the problems. As a matter of fact, a quantum computer is quite limited in what we are able to have it doing. Perhaps in future it will be able to solve also problems, more complex problems. But what we can do is to solve the problems we see today. So that will be what we shall see tomorrow. Any questions, requests, or things you might be interested in, perhaps to discuss?
Nothing. It was all clear. Thank you.
Okay, you're welcome. For today, I will say that. That's it. So see you tomorrow.
See you tomorrow, Professor.
Sir, thank you. Yes.
Thank you. Bye bye.
Bye. Secondo me devo fare da lì, no?